Hello, Chem 1B. This is Chapter 15, Lecture Video 1, and we're going to be talking about chemical equilibrium, honestly, for the next 3 chapters. So this is the most general type of chemical equilibrium chapter, and then after that we get into specific types of equilibriums, like acid-base or solubility later on. So what is equilibrium? Equilibrium is defined as when the forward and reverse rate of our reactions are equal. Or in other words, the rate of formation of our products is equal to the rate of formation of the reactants. So you can kind of think of this in terms of the forward reaction and the reverse reaction. Forward reaction's rate is going to be equal to the rate of the reverse reaction for a chemical reaction. It's dynamic. Rates can change, and equilibrium will usually try to counteract those changes to get back to the state we know as equilibrium. When we're at chemical equilibrium, we usually use specifically a different type of arrow when drawing our chemical equations, right? You can kind of see this arrow here is a double-headed arrow. And usually it's a double half-headed arrow like shown in this picture. This means basically that this reaction will eventually reach chemical equilibrium or is at chemical equilibrium, depending on the context of the situation. How is equilibrium related to reaction rate? We talked a little bit about this near the end of chapter 14 with our mechanistic steps and how we could rearrange those based on the equilibrium setup that we had in some of those problems. A little bit more, kind of revisit that. What is the rate law for this elementary step, right? A is our reactant, B is our product, so we really only care about the A in this reaction. So our forward rate of the reaction would be rate is equal to some rate constant times the concentration of A. If this is my forward reaction, this would be the rate law for the forward reaction. Or in other words, our forward rate. If we flip this reaction around, though, we have B going to A. And this is kind of like the reverse reaction. And if we want to write the rate law for this, we have a different rate constant. Usually we indicate K to the -1 to indicate that we're going in reverse. We're talking about a reverse reaction. It's times the concentration of B. And that's equal to our rate of the reverse reaction. Now, at equilibrium, we know we can set these two rate laws equal to each other because the definition of equilibrium is that the rate of your forward reaction is equal to the rate of your reverse reaction. So for an equilibrium where A goes to B and vice versa, right, back and forth here, we have the rate law for the forward rate is equal to the rate law for the reverse rate. Now, often we rearrange this situation in order to get all the constants on one side and all the concentrations on the other, right? So here we have a constant, this K value here, and this K value here is a constant. And here we have our concentration of B and our concentration of A. And we want them all on one side respective to each other. So if we rearrange it, we get, this situation here. Now, on one side, you can kind of see we have the rate constants right there. And on this side, we have the concentrations. Now, we define a new thing known as the equilibrium constant, which is unfortunately also symbolized by a K, except this time it's a capital K, where rate constants are lowercase k's. And the equilibrium constant is defined as two things. Typically, less frequently, is the forward rate constant divided by the reverse rate constant. But this is a totally acceptable definition for our equilibrium constant. Or it's defined as the concentrations of the products divided by the reactants. Remember, if we look at our reaction over here, B is a product and A is a reactant. So it can also be defined in terms of concentration. Now, there's a little bit more to this. If there was a 2 in front of this B, we would have had to have squared this concentration of B as well when we write out the expression. But that's the gist, and we'll talk more about the rest as we go on. But again, this capital KEQ is known as the equilibrium constant, and we're going to be spending quite a bit of time talking about it throughout. Equilibrium constants can be defined as the ratio of the forward rate constant over the reverse rate constant of our reaction, or the products over the reactants. Like rate constants, equilibrium constants are independent of concentration. So if I change concentration, the equilibrium constant will not change. However, just like rate constants, again, they are dependent on temperature. So as temperature changes, our equilibrium constant will change. There is a small difference here, though. In chapter 14, we learned that rate constants, as temperature increases, the rate constant increases. With equilibrium constants, there's no such certainty. Sometimes raising temperature will cause the equilibrium constant to increase. Sometimes it will cause it to decrease. This depends on mostly whether the reaction is endo or exothermic. So we can always write an equation for our equilibrium constant directly from a balanced chemical equation, right? So again, the lowercase letters in this equation are all our stoichiometric coefficients, and the uppercase letters are going to be our actual compounds and molecules. So if we do that, our equilibrium constant is always going to be equal to the concentrations of the products, these guys, on top, over the concentrations of the reactants in the denominator, as you can kind of see here. Now, each concentration term is taken to the power of this stoichiometric coefficient, right? So whatever number is in front of our compound, that number becomes our exponent in our equilibrium constant expression. So let's go into this a little bit more. One of the things that we should ask ourselves is, why are we allowed to use stoichiometric coefficients as exponents? And the reason we're allowed to is that we assume that all equilibriums are elementary steps. Now, while this isn't entirely true, it is most of the time true, and for the most part, it still yields make this assumption. So this slide is a little bit wordy, but when we want to figure out what the units of the equilibrium constant are, it's pretty simple. There are no units for the equilibrium constant. Now, why is that the case when we have concentration units in our equation? Is actually due to the fact that we kind of force it to have no units. We take all of our reactants and products and divide by their standard state at a given temperature. Now, this is something you probably learned about in Chem 1A in chapter 6 or in the thermodynamic chapter. But at 25 degrees Celsius, standard states are defined as, if it's a solution, it's 1 molar. If it's pressure, 1 atm. And if it's a pure substance, then just their pure value. So what this all means is that if I have a concentration term in this equilibrium constant, by definition, I'm dividing it by 1 molar. And this guy's in molarity, so the molarity units, they're going to cancel here. This guy's in molarity, molarity units are going to cancel. Molarity, molarity units are going to cancel, so on and so forth, right? Yielding an equilibrium constant with no units. And this is always the case. Our equilibrium constants do not have any units. If some of this up here is a little bit difficult to kind of understand, don't worry about it. This is the most important bit on this slide that you need to know about. Our equilibrium constant does not have units. It's one of the few times where you can write a number and be okay when you don't put units next to it. Points at least. Because it's correct. If you put units, you'll lose points. So what if our reaction involves gases? In our equilibrium constant, so far, I have shown it as, our concentrations of C times the concentration of D to the power of lowercase d and lowercase c all over A's concentration and B's concentration. Well, most of the time we use concentration, if we're being honest, because most reactions are in the aqueous state that we cover in Gen Chem. However, it is totally applicable, we usually call them KPs, to instead of using concentration, use pressure. So if these are gases, let's say A, B, C, and D are all in the gaseous state, then you can do the same thing, but with pressure. Now the pressures do need to be in ATMs, but otherwise it's totally acceptable to use either one of these expressions. As long as your substances are all in the gaseous state, it's okay to use KP. Now, this is important because it's actually going to give you two different numbers, whether you divide the numbers in terms of concentration or you divide in terms of pressure. That changes your actual values. So we need a way to convert between concentration and pressure. And the easiest way to do this is using the ideal gas law. PV is equal to nRT. We know, hopefully, that molarity is moles over liters, right? So I need a way to get a molarity term in this equation. Now I know N is in moles and V is in liters. How convenient. So if I want to get a molarity term in this equation, I need to have moles over liters like I have there. Or in other words, I need N over V, because that's the same thing as molarity. So we need to rearrange this equation to get that. So let's do that rearrangement, and we get P is equal to N over V times RT, where this is really just your concentration term. This allows us to convert pressures to molarity and molarity to pressure, assuming the substance is in the gaseous state. RT, as long as we don't change temperature, is going to be a constant, right? Because R is 0.08206 ATMs times liters over moles Kelvin. And T is just our temperature, but it has to be in Kelvin units. All right. So let's look at this equilibrium equation or reaction. We can write an equilibrium expression in terms of pressure for this reaction or in terms of concentration. And we're allowed to do it in either case. In this case, because everything's in the gaseous state, we could write this in terms of pressures. So I could write my equilibrium constant in terms of the concentrations of each component, right? Concentration of NH3. Remember, it's always products over the reactants. So I'm going to take my product here, put it in the numerator. Because there's a 2 here, I need to put the 2 exponent there. I can take these reactants and put them in the denominator. And again, because there's a 3 here, we need to put that cubed above the H2. Now, all of these can be also used instead of concentration in terms of pressure. So we could have also written this like this. Now the 2, you can kind of see here, have different subscripts next to their equilibrium constant. The C means that this is the equilibrium constant in terms of concentration, and the P means that this is the equilibrium constant in terms of pressure. But effectively, if we look at these two equations, they're pretty much the same thing, just different in terms of how we actually write them, right? We have pressure here, we have concentration with the brackets there, but otherwise the same things are squared, the same things are cubed, the same things are in the numerator, and the same things are in the denominator. But these are going to give you different values, right? This value here, whatever it is in terms of concentration, will be different from this value here in terms of pressure. So there needs to be a way that we can convert between the two different equilibrium constants. We should be able to, in other words, convert between Kc and Kp. And we can do that using our ideal gas law here, and the way we rearranged it on the previous slide. So one thing I could do instead, right, since this is just really our concentration term, I can say, hey, well, pressure here of, let's say, NH3 is just equal to this being concentration of NH3 times RT. Quantity, cubed, because there was that cube around the NH3 concentration or pressure term. So if I just kind of plug this in here, this bit in for each one of these pressures, I get this equation where I have RTs in there and concentrations instead of the pressure. Well, let's see if we can simplify this expression a little bit. I notice that there's a lot of RTs in this expression, and I can factor them out, right? Really, this is NH3 concentration squared times RT squared over N2 concentration times H2 concentration cubed times RT to the power of 4, right? Because this cubed here times this gives me to the power of 4. Well, if we look at that, right, these RT squareds here, they cancel with the RT to the power of 4 and give us just RT. Here, I'm just going to rewrite it down here. To the power of 2 in the denominator, which brings us to here. Now, what's this term look like, right? We've seen it somewhere. In fact, on this slide, hey, look, that's the same thing as this. So I can now substitute in, hey, Kp here is equal to Kc divided by RT squared. Now this has created a relationship where I can say, hey, Kp is equal to Kc over RT to the power of 2. And now I have an equation that allows me to relate Kp to Kc in this instance. Now, does this work every time? No, because if we changed our stoichiometry coefficients, we'd get a different equation. This in terms of something else, right? If the equation wasn't the same, we'd have to come up with an equation that would work for any generic equation, right? And so we have all that. We can calculate Kp here. These are all the equilibrium pressures, so I could just plug these in, right, to the expression. And if I do that, I get, this value here of 2.79 times 10 to the negative 5. I actually already edited it. This is the generic expression between Kp and Kc that allows us to use it for any individual reaction. Doesn't matter what it is. This will always work. Delta N gas here is really just equal to the moles of gas products minus same thing, but reactants. Right, so in this case, I have 2 moles of gaseous products and 3 plus 1 mole of gaseous reactants. In other words, delta N gas here for this reaction would be equal to 2 minus 4, or in other words, negative 2. So Kp is equal to Kc times RT to the power of negative 2. Now, if we're at 472 and we have all that other information, we have Kp, we can actually say, hey, 2.79 times 10 to the negative 5 is equal to the ideal gas constant times 472 in Kelvin, taken to the power of negative 2. And I can just rearrange this equation. This is just me rearranging it a little bit and get my Kc value. But what do these numbers really mean? Now, equilibrium constants, we'll get into what they actually mean in the next lecture video, but let's do just another example here really quick. We have that equation, right? Kp is equal to Kc RT delta N gas. And we can use that to solve for this problem. Okay, so we know Kc, right? We have this value. We know R because it's a constant, it's always given. We can solve for temperature. We got to change 50.5 Celsius to Kelvin, which gives us 423.7 Kelvin, right? And at that point, we need to get what delta N gas is. Well, I have 2 moles of gas here on the product side, and I have 1 plus 2 on the reactant side. So my delta N gas is going to be equal to 2 minus 3, or in other words, negative 1. It's not always negative, by the way. So if I wanted to solve for Kp, I'd go, okay, Kc is 3.25 times 10 to the 2 times 0.08206 times 423.7, all to the power of negative 1. I'd multiply that out, and I'd get Kp. And what we get is 9.35 as my Kp value. Or in other words, B is my correct answer. So if you have any questions, just let me know. This video was a little bit longer. I'm sorry. Discussion, email is the best way to get a hold of me.